So in a good follow-on to Charlie's presentation, I'd like to introduce Dr. Timothy Nelson. He is up here visiting us from Florida. You heard originally in Henry's presentation about the work that was being funded by the National Park Service, being conducted by the folks in the Netherlands, Deltares. And Tim is the USGS technical person who's working with them on that project. As you can see, his affiliations, USGS, he's from St. Petersburg, the Coastal Marine Science Center there in Florida. So he's going to fill us in on some of how that project is going and some of the early results. It's looking at both the downdrift sand transport and modeling the morphogenic evolution of the inlet, hopefully to be able to use that in a predictive manner in the future.
So I'm going to talk about what the USGS has been doing in response to Hurricane Sandy studies on Fire Island. This is going to deal with both the nearshore area as well as in the breach itself. And also about our development of a breach morphodynamic evolution model, which is in cooperation with Deltares. We're taking a multi-step approach to this study, basically dealing a lot with field work, analyzing the data, and trying to develop tools to predict the influence of breaches in the future. The first one I'm going to talk about is quantifying and characterizing the morphologic response and recovery of the breach system. We have performed a total of 17 surveys of beach profiles at set locations each time along Fire Island. These go from pretty much the top of the dune all the way out to as far as we can walk with basically a wheel and a pole on the GPS. These have been conducted multiple times, and all this data is put online. When you can look at the change of these profiles over time, and also look at some characteristics to see how are the profiles changing in response to Hurricane Sandy and in the recovery process. Look at things like the volume and see that over time you show the initial volume drop due to Sandy and then the gradual increase as it's recovering. In addition, we're looking to quantify and characterize nearshore sediment budgets. In June 2014, we performed a large-scale jet ski survey of Fire Island. We collected pretty much transects about 100-meter spacing on average throughout the entire island, and detailed measurements in the breach. So we had 2 jet skis outfitted with echo sounders and used post-processing of the GPS data. From this, we were able to get a good bathymetry map, which allows us to look at the spatial extent of various features on the near shore and shore face, as well as in the breach, and also look at the overall profiles and determine certain metrics dealing with the nearshore bar morphology and the profiles. From this, we're looking at things like the distance from the mean high water line to the bar crest, getting an indication of basically the width of the surf zone, the depth of the bar trough, the depth up to bar crest, the volume of the bar, the height of the bar steepness, the slope of the entire bar to the mean high water, the slope of the bar crest to offshore, and the slope of the bar crest again in the profile, as well as any other characteristics and metrics we can obtain from these profiles. And then we're looking at these for both pretty much all parts of Fire Island, including the west, the central part of Fire Island, which shows some interesting characteristics at the moment, and then the east. And we're also comparing these to previous profiles done prior to Sandy to see what has changed with time. We're also doing other aspects. One other aspect, we're developing a data-driven model to understand recovery to storm response. And this is a Bayesian type model, which is being basically created using prior storm events. And then we're going to run it for Hurricane Sandy and see how it responds and make adjustments and improvements. So all these various model development and field work is being put together to test and refine predictive models, both the event-based storm response and post-storm recovery process. Our overall goal here is to develop tools for forecasting vulnerability and response and recovery. And this is not just related to this breach, the wilderness breach, but any breach that can occur. This can be plugged into a model and used for any time a storm approaches, determine where a breach will occur and how it will develop. Part of this, developing this tool, is required to quantify and characterize some of these near-term morphologic evolution of the breach. So in June 2014, I said we had a jet ski survey. In addition, we also had ground-based LiDAR from the Alabama Water Science Center, and we also did a backpack walking of the breach and shoals to get into the very shallow areas. So we were able to get a really detailed image or bathymetry of the breach itself in June, as well as the coastal areas surrounding it. We captured the flood shoals, ebb shoals, and as well as the channel nicely. In October 2014, we went out with another jet ski survey and focused on the Great South Bay area, as well as doing a repeat coverage of the breach and coastal area. So we did pretty good detail of Fire Island Inlet, Narrows Bay, the eastern side of Great South Bay, and Bellport Bay. This is helping us to get some characteristics of what has changed since Hurricane Sandy, as well as some model inputs. So we're able to get a nice bathymetry to identify channels, as well as shallow areas and morphology in the breach. Also, in addition to that, we've been collecting breach discharge velocity and bathymetry has been collected by the USGS New York Water Science Center. They've conducted numerous surveys, often in times corresponding to when we were out there doing profiles as well as measurements. They're collecting water velocity and depth. It was measured using a Sontec M9 acoustic Doppler current profiler and an Ocean Science remotely operated Q-boat. So they're able to just set this boat in the water, do transects 2 hours before high tide and 2 hours before low tide in several parts of the breach. So they were able to determine measurements of the discharge and velocities during flood and ebb. This is from one of their reports online from the 6th of November 2012, just shortly after the breach formed. And then discharges from 13th of November 2013. So just in that pretty much 1 year time, we can see both the change of the breach itself, the morphology of the breach, the width of the breach increase, as well as determining what the volume of the discharge rates are. In addition, in October 2014, we did numerous sediment sample grabs and to find out what the grain size is and get better control over that. So we did surveys just outside the breach, just near the ebb shoal, in the breach channel, and in the flood shoals. The last part of this study is being done in cooperation with Altaris, Martin Van Ordement, and we're working on creating a numerical model to describe and define the hydrodynamics of the barrier bay system. So some of the science questions proposed for this study is what processes govern the morphodynamic development of the breach, and how will the breach evolve? Can we build a tool that can be used to predict breach evolution? So instead of having to run this long-term simulation, something simple that can be run and speed up the simulation process. And how does the wilderness breach affect surge levels and inundation in Great South Bay, both during Hurricane Sandy and in subsequent storms? To do this, we're using the Delft 3D modeling, numerical modeling software. It's a state-of-the-art modeling framework for hydrodynamics, water quality, ecology, waves, and morphology. It incorporates numerous modules. The ones we're focused on are the hydrodynamic module, morphological module, wave module, and sediment transport module. For the moment, we're not including the ecological or water quality. We're using several nested model grids. The reason for this is the larger grids allow for hindcasting of historical storms, as well as determining storms that occur nearby that may have disturbances that propagate into the study area. The largest model incorporates the Northwest Atlantic. It has grid spacing of 0.025 near the coast to about 0.1 meter or 1 degree offshore. It's an unstructured mesh. The bathymetry we're using is from the General Bathymetric Chart of the Oceans, GEBCO, and the Coastal Relief Model. The next model is an unstructured mesh with spacings of 1.5 to 10 kilometers in the U.S. Northeast, and we're using bathymetry from GEBCO and the Coastal Relief Model. Getting finer still, we're going down to just the New York region, and this is an unstructured mesh, finer spacing of 30 to 200 meters. And we're using data from the Coastal Relief Model again, as well as NOAA navigation charts and USGS bathymetric data. Still going one more step now. We're going to the fourth nested model, which is the Great South Bay and Coastal Model. This is a curvilinear structured grid, and we're using bathymetry measurements from the Coastal Relief Model and Hurricane Sandy USGS composite data. We also have additional data which we're plugging in at times and also for model comparison. So we're using the coastal relief model, national elevation data sets, the USGS pre-Sandy composite, but also we have more data from October 2014 for the Bay using Great South Bay, Fire Island Inlet, Narrows Bay, Belport Bay, and also to determine the basically how the model is responding morphologically. We have the wilderness breach from June 2014 as well as the recent October 2014 data. In order to test the model response and make sure it's valid, we ran the simulation using just tides and wind during Hurricane Sandy and looked at water levels in the Battery and Kings Point. And it doesn't seem to be running. Okay. Can I step at least? All right. Well, anyways, if you look at the top part up here, we're looking at the water level for the Battery, computed, which model results is in black, observed is in red, and the model agrees well with the observed data for Battery and Kings Point. It also shows characteristic response of the set down in the bay during the storm. All right, looking at the other storm surge from Atlantic City, we see pre-Hurricane Sandy, the tides match up very well for Atlantic City and the Battery. Also follow the same trend for Atlantic City and the Battery during the storm. There is some differences, and it's important to keep in mind that waves were not included in these simulations. This is just tides and wind. Looking at what happens in Great South Bay from Lindenhurst and Belport, as Charlie Flagg was talking about earlier, we see this model, the set down that was observed in Belport. And of course, with all the wind blowing towards Lindenhurst, we do not see that set down during that time. So we are observing what does occur. So this gives us confidence that the model can be used to run boundary conditions for the breach model itself. So the breach model itself contains is over the breach area of includes 15-meter spaced grids and is over about 8 kilometers in length. We're using coastal relief model pre-Hurricane Sandy bathymetry for the Bay, and pre-Hurricane Sandy composite USGS data for the coastal area. The breach model includes schematized tides, which are the bay boundaries, as well as the ocean boundaries. Waves are run with SWAN using a schematized climate. Sediment transport module used is Van Rygen 2007. At the time of these simulations, this was prior to October survey, the model was still run using the default grain size and delta of 200 microns, which is much smaller than what was actually observed there. And it's also using a Morphac scale, which is basically allows the model to be run in about 1 month, but incorporate about a year's worth of data. Based on the wave climatology, basically the larger waves, which occur less frequently, have a small Morphac. Smaller waves, which occur more frequently, have a larger Morphac. Now let's see if this animation will work. So this is the breach model with just 1 year, tides only. Okay, this is showing the development of the breach, and we see some of the characteristic images that we see in Charlie Flagg's photos. We see that we see the channel, we see the nice flood shoals developing, but there are some differences still at this moment. This is just tides by itself, and we do not see a very well-defined ebb shoal. Also, the flood shoals are way too large to the overall structure, much larger than what should be or what is observed. Plus, the channel is much wider and deeper. Now, if we add waves, but qualitatively, this does agree. We do see the same overall features. We do see the channels present. We do see the flood shoals developing. There's good characteristics overall. Some differences. Now, if we do just 1 year with tides and waves, the channel becomes narrower and becomes better confined as we actually observe. We see this development of the season or this occasional spit that is observed in the data or in the images. And also the flood shoal is much smaller, getting closer to what was more realistic and would observe. We still don't see the ebb shoal forming though. So there's still work to be done on this model. It's coming along. There's been some changes in the way that the wetting and drying has taken place in the breach in order to better improve the where the channel is and make it behave more like what we're actually observing. So we have a lot of future work to do. So far, we've been primarily heavily involved in data collection. And we're going to have one more huge data collection to occur in the spring, which will do a whole nother shore face morphology as well as the breach using the jet ski systems, which allows us to get all the way into the surf zone and into the shallow areas of the breach system, as well as getting people on with backpacks walking the shallow shoals. We're going to continue the development of the metrics for the predictive models, both for the beach profiles as well as the shore face metrics, and continued refinement of the breach model itself. We're going to use improved bathymetry. Currently, the bathymetry for the bay, the coastal relief model, is much older than what we care to use, so we're probably going to be trying to see what happens if we use some of our October survey data, assuming maybe not as much has changed in the Great South Bay during Hurricane Sandy. We're also going to include seasonality and wave climate. Right now it's just a schematized wave, so we're looking at an entire year and just adding them all together, but looking at seasonal variations, especially which may be related to that spit formation. Also include spring neap variations instead of just one sinusoidal schematized tide, and adjust the mean water levels in the bayside boundary. Right now it's just overall mean level, basically using more real-time values. Also adjust the grain size and test multiple fractions. Using that 200 micron grain size is most likely the reason why the ebb shoal forms as fast, or the flood shoals are as wide as they are and form as fast as they do, and the channels as deep as it is. Once we increase that, the sediment transport should be less, and it'll give something more realistic. Also run full-time series of water levels, waves, and winds. Right now, instead of schematized, run real-time and see, do we capture all these different changes that occur and compare it to our surveys. Validate the sediment volumes, fluxes, and hypsometry, etc. Right now, we're still in the final stages of QA/QC on all those surveys, but we plan to look at what has changed volumetrically in the breach itself, and also then define the skill metrics. So how are we going to go ahead and say this model works and doesn't work, where it's good at, where it's not, compared to our survey data. So that's currently the state of what the USGS has done. As one point I didn't mention, but Charlie mentioned, we did also have use the Army Corps' LARC system for one of the surveys. They were also out there in June collecting bathymetry. That's something we'll also be comparing it to look into the breach morphology. All right. Any questions?
Are you actually modeling the breach process, or you're modeling the, just after the opening, occurred?
Right now, we're just looking. Okay. He was asking if we're modeling just the breach evolution or also the occurrence of the breach. At the moment, we're focused on just the evolution of the breach itself. Don't know if we'll add in the breaching process or not at the moment. I think it's something we're considering, but depends on time. Okay, I think someone over there had a hand raised. Okay.
Tell us about the wind field that you use to drive your storm surge model. And the second question is, why does adding waves to the wind decrease the size of the flood delta?
Good questions. Martin Van Orme is one who's been running this model, so I don't know all of his parameters. I know recently we have just obtained wind data from weather flow. I think that's what he was using. I'm not sure if it was an older buoy data, but we are working on trying to get better wind variables. And the other question was the waves.
What waves reduce the size of the delta?
Yeah. I don't have a good answer for you at the moment. I would be happy to get back with you once I talk with him.
Do you have pre-breach bathymetry that you're comparing even what the post-breach bathymetry to see what the volume of the flood tidal delta is and the ebb tidal delta?
Unfortunately, we do not have it all the way into the breach. We have the Earl flew 2 days before, so we have some of the data for that area, but not all the way back into the flood shoals.
So you can't really say how much sediment's been trapped in either shoal?
Not from before, but we're having several surveys afterwards. So we'll have 3 surveys we compare recently just from June itself.
I have a question.
Okay.
So with the modeling, the big question for this breach since it occurred was, is it going to change? Is it going to close?
Mhm.
And might it close? How would it close? What within the model, what parameters in the model would most likely have to change to have that happen? Can the model actually predict that it would close, or if it would close?
Another good question.
Would you repeat the question? for
Yeah, the
everybody?
question was, are there any parameters in the model that will allow for it to close, and what would those be? I know Martin has been tinkering with the different parameters. We haven't run it a long enough time. At the moment, we're still running it shorter periods to try to validate and get the parameters correct. So I don't think we have an answer for closing yet. But hopefully that's something that the model may be able to incorporate.
Anything else?
I would think that the longshore drift of sand from the east would be a big factor of how many drifts is that from issue.
Yeah, that is probably an important one, yes. So, I know we're also looking at...
The source of sand is going to shovel in there, but one flows up by itself.
Mhm.
It's got, zero longshore drift.
Yeah, I don't think we're incorporating zero longshore drift or incorporating that in there. So that in the direction of the storm too probably plays a large part, possible closing.
Should I ask, maybe I missed it, are you modeling Mauritius Bay also and Mauritius Inlet?
We're not modeling Mauritius Bay. We're pretty much stopping it at the Narrows Bay, basically assuming that is a boundary condition.
Because it's really kind of a three-inlet system with
Oh, it's
Fire
not.
Island, the new
It's not really
inlet,
responding.
and Mauritius Inlet.
Okay, I'm sorry. Can you repeat that? I'm sorry, I was trying to get the
I
slide.
just mentioned it. In reality, it's a three-inlet system with Fire Island, the new breach,
Mhm.
and Mauritius Inlet connected by that channel below Smith Point. So
Well, I guess I should rephrase that. Our Great South Bay model does incorporate Mauritius, Fire Island Inlet, and then the breach. Our breach model itself, we're just focusing on the boundaries run by that model. So yeah, we are incorporating Mauritius Inlet.
Just can you give an estimate on how long it would take as far as the computation time to look at 1 day of evolution of the breach?
1 day evolution. All right, he's basically computation time for about 1 day evolution of the breach. At the moment, I think I was trying to run it for the June data that we had during that time period, and it took maybe 30 minutes to run for about 2 weeks worth of data. So doesn't take long to do the computations. That's using a Morphax scale still, so we're still working on getting more of the real-time data.
What type of information would you need regarding grain size to determine a closing event in the model? What would you need to do that? It's going to be predictive to closure. What would you need?
Well, the grain size we were primarily using for the sediment transport aspect. So right now, like I said, initially it was just run the normal default method. Where you're going to be testing it further with the new grain size that we collected, plus using grain size distributions. So as far as grain size for the closure, it's more so just the sediment transport rates. Charlie?
Hi. This is by no means a criticism. The model is rather impressive. But one of the things I noticed about the breach evolution in your model was that it remained straight across the island. The characteristic breaches around here rotate clockwise. And it didn't, maybe it happened too fast and I didn't see it.
Yeah, that is something we've seen. Part of the aspect or thinking is because we're not taking seasonality into account. We're just using a schematized climate and sinusoidal tides. So once we start actually using more real-time or seasonal impacts, we expect to see some more variation than just a straight channel.
Charlie, isn't one longshore drift a big part of that? If you look at Fire Island in there, it's grown 5 miles in 100 years. So that east to west longshore drift is an important part to explain that. Joe, you're the expert.
taking no, he talked about that. It's long short drifts, but we are taking one more question from Chris.
Tim, I'm just wondering if the model's at a stage where you're able to see anything with regard to flood dominance versus end dominance, because we do see evidence that I suspect Charlie's seen it in his data, and we've seen it in our discharge measurements as well, but we do seem to have a much greater peak flood than peak end.
I think the model is pretty much just about there. We're trying to validate it against some of the discharge and volume, velocity measurements to make sure we're getting what's on the right order of the ballpark in all of our settings. So that is something we will be able to tell.